Hello everyone, let's discuss negative hypergeometric distribution. Let's take a population which has n number of items. Among them, m are the items with certain characteristics and n minus m are the items without any certain characteristics. If you consider this case, let's suppose x be the number of draws and r be the number of successes. When I say success, that means the when we draw something out that has that certain characteristics, that event is known as success. Now let's understand what does the negative hypergeometric distribution actually measures. Negative hypergeometric distribution is the distribution of sampling of objects without replacement till a fixed number of objects having a certain characteristics is obtained. That means if we consider the previous case where I said x is a number of draws and r is the number of success, then that means we draw items from the population until and unless we get the required or the suggested number of objects with a certain characteristics. Okay, it's in the previous case when we are talking about hypergeometric distribution. Then we talked about that the distribution of hypergeometric distribution try to find out in how many ways can we draw items of certain characteristic from a population. But here the number of drawing certain items, certain characteristics, which is defined as the number of success, is fixed, but we can have any number of draws for that. So there is defined a new PMF for negative hypergeometric distribution, which looks like this. So here x minus r minus 1 times n minus x, m minus r, and n by m. Now what does this mean? So you can see we have x is the number of draws, r is the number of successes. So we already know from the negative binomial distribution that this kind of combination doesn't give us particular unique values or unique distribution for each probability. That means that's why we have to put a minus sign here always. So you can think of this negative hypergeometric distribution as a combination of hypergeometric distribution as well as a negative binomial distribution. So we got this first term. Second term, just like hypergeometric distribution, we get m minus r, that is these refers for the number of draws from the total items in the population, and this refers to the number of total items taken out which has certain characteristic from the total amount of items that has that certain characteristics. Okay, so this is the product of these two combinations, and dividing it has the NCM, that means among the total combination how many of the items among the total items how many of them have certain characteristics. So this is all about negative hypergeometric distribution. So now let's talk about moments of it. Now since again it doesn't involve any probability term, so we don't try to find out the moment genetic function of it, but rather to use expectation concept to find out the moments. So let's see this. Okay, so moments of negative hypergeometric distribution. Expectation of x equals summation of x equals 0 to n x px. Then I substituted the value of p of x. When I put that in here, I consider z to be 1 over NCM. Z is a constant. We do not have any x term. Get out of this summation sign. Now here x times x minus 1 becomes x factorial. Now we have r minus 1 factorial. So I multiplied r on both numerator as well as denominator so that we can get a value which looks like z equals z times summation of x equals 0 to n x factorial, and now r, we don't need r here, so we can take zr, and we have z minus r factorial, and n minus x c m minus r. This becomes c x r m minus x c m minus r. Again, using property of product of two combinations, we can write it as n plus m c m plus 1 times r by n c n ncm, sorry. Then it becomes okay, so r n plus 1 factorial by n plus 1 minus, that is n minus m factorial times m factorial by n factorial m factorial, no, not n minus m. Is it n minus m? Wait a second, I'm confused here. Okay, yes, we also have m plus 1 factorial, and we have also have, I think it goes up, right? Okay, let me write it correctly. So we have r times n plus 1 c. That means n plus 1 factorial n plus 1 minus n minus 1 factorial times n plus 1 factorial times m factorial by n factorial. N plus 1 factorial is n times n, wait a second, n plus 1 factorial is n plus 1, wait a second, n plus 1 factorial, right, equals to n plus 1 times n factorial. Okay, n factorial, and m plus 1 factorial is m plus 1 times m factorial, and we have got this and this are cancelled, so m minus 1 also. So what I got is r, n and n cancelled, m and n are cancelled, so n plus 1 m plus 1 and times n minus m. Am I correct? Let me check. No, I am not correct, because somehow this also get cancelled and we only get this. Just figure out how do we get that. Okay, now so we have got our expectation, that is expectation of x equals r n plus 1 by m plus 1. So this is our mean. Now let's see how do we find the variance. For the variance, we do the similar thing that we did in the hypergeometric case. So expectation of x squared equals expectation of x plus 1 minus expectation of x. Now you might remember in the previous case, in the case of hypergeometric distribution, we had written x minus 1 and we had a plus sign there, but we have x plus 1 there because I will because you will understand that later on in the equation. So after that, we first try to find out this equation using this formula. Similarly, now in the same as the previous case, I considered z to be 1 by ncm here. Okay, so g is taken out if it is not visible to you. So the denominator part of it has already been used as z. Now what you might want to do here is you want to open this combination form, and after opening this you would get something like this. Now to cancel x plus 1, we do some calculations here, some rearrangements, then we get r plus 1 to make this r plus 1 factorial, and it's a constant, and we get this is following here. Now after that, yeah, so after that this is a constant, so we took it out. Z is already a constant, so we have got two constant, and from the properties of summation and product of summation of two combinations or product of two combinations, we got this expression right here from the previous one. Then I opened it and then I get this thing. After this, yes, so after that, on further inspection, we got this. This is expectation of x, x plus 1 equals this. Now we have to minus the expectation of x to get expectation of x squared equals this thing, r plus 1 m plus 2 by m plus 2, then n plus 1 by n plus 1. Now yes, and then minus expectation of x. Now what have we got as expectation of x? So we have got r n plus 1 by m plus 1 all squared. Is it? No. So this is what we get as expectation of x squared. Now variance is expectation of x squared minus expectation of x whole squared. So we can write it as this time r plus 1 m plus 2 by m plus 2 m plus 1 m plus 1 minus r this minus r squared whole squared. On further, now this is what the variance is. On further calculation and cancelling, what we finally get as a variance is this r n plus 1 and minus 1 m plus 1 minus r by m plus 1 whole squared m plus 2. This is what we get as a variance. So this is it about the negative binomial distribution, negative hypergeometric distribution. We will do continuous distribution next week. Okay.